Learning outcomes. After studying this module, you shall be able to learn about solution kinetics, learn about ionic reactions, learn about the effect of solvent on the rate of the ionic reaction, and know about ionic strength. In our previous module, we did talk about Linneman's mechanism for unimolecular gaseous reactions, and we did derive the rate law expression using steady state approximation. And up till now, in chemical dynamics, we have only considered gaseous phase reactions. Now the question arises how to study kinetics of reactions that take place in solution phase. This forms a separate class of kinetics which is commonly referred to as solution kinetics, which forms a part of discussion of this module. So in this module, we will study solution kinetics and we will look into various parameters that affect the rate of a solution phase reaction. Solution kinetics. Solution kinetics is the kinetic study of chemical reactions taking place in solution phase. Such reactions are very common, but it becomes difficult to study such reactions theoretically the way we did for gaseous reactions, because solvent over here plays a very important role. There are two important solvent dependent parameters which affect the rate of the reaction, namely dielectric constant and viscosity. In gas phase reactions, both these parameters, that is viscosity and dielectric constant, are not there, and therefore the gaseous reactions have been studied theoretically with ease. However, the situation is very much different for solution phase reactions, and therefore we need to consider them separately. Now let us look at solution phase reactions. In general, the solution phase reactions can be classified as ionic reactions and non-ionic reactions. For ionic reactions, we have the example H plus plus OH minus giving H2O, and for non-ionic reactions we have methyl bromide reacting with hydroxide ion giving methanol plus bromide ion. Over here, we will be basically focusing on ionic reactions where we will see how the solvent affects the rate constant. Now, let us take up the kinetic study of ionic reactions, or we can say that we are talking about solution phase reactions. Now, let us consider the reaction A plus B giving product P, where A and B are ions respectively. According to chemical kinetics principle, the rate of this reaction can be expressed as rate is equal to rate constant K into concentration of A into concentration of B. Now, we need to see whether we can apply the chemical kinetic theories so proposed earlier for studying gaseous reactions to determine the rate constant for ionic reaction. Now, for this, one can try the following routes to determine the rate constant of ionic reactions. Number one possibility, or the first possibility, is collision theory, which we have already studied. Now, as per collision theory, the rate of a reaction so proposed A plus B giving products can be expressed as rate is equals to ZAB into e to the power minus E naught by RT, where ZAB refers to collision density or total collision frequency, that is the number of collisions that occur per unit volume per unit time. Now, this ZAB is further, as can be seen, is dependent on collision cross section, number density of A and B, and the average velocity. So, for gases, what we found that ZAB is easily calculated, but for ions it is very difficult to determine ZAB in solution phase, since there are various parameters like charge on the ions, the dielectric constant of the solvent, etc., due to which the collision diameter and threshold energy E naught cannot be determined exactly, and therefore ZAB cannot be determined exactly. So it becomes difficult to apply collision theory to solution phase reactions. Now, the other possibility is transition state theory. We have studied transition state theory earlier via two different approaches, classical thermodynamic approach and statistical thermodynamic approach. Now, the rate constant expression for the reaction A plus B giving product obtained via these two approaches is taken one after the other. Firstly, we will look into the statistical thermodynamic approach, where the rate constant for the reaction is expressed as partition function of the intermediate upon partition function of A into partition function of B into e to the power minus delta E naught by RT into Na into kBt upon H, where Kb, R, T, Na and H have the usual meanings that we have discussed earlier. Now, as can be seen from this equation, the rate constant is dependent on partition function. The partition functions are defined for gas phase, where particle-particle interactions are not significant and are hence not considered. These gas phase partition functions cannot be used for species in solution phase, as particle-particle interactions become significant in solution phase. Therefore, we can say that the statistical thermodynamic approach cannot be used in solution phase to determine the rate of a reaction or the rate constant. Now, the second approach is the classical thermodynamic approach of transition state theory. And as per the classical thermodynamic approach, the rate constant is given by the expression K is equal to RT upon H into Na into C naught into e to the power minus delta G naught upon RT. Now, over here, the most significant parameter is delta G naught, which is the change in Gibbs free energy. And with the help of this, we can use this equation for determining the rate constant for ionic reactions. So, this equation is used for determination of the rate constant and hence the rate of the reaction in solution kinetics with some modification. And we will be using this equation with some modification to study the rate of ionic reactions. Now with this, let us now start with bimolecular ionic reactions. Let us consider a bimolecular ionic reaction proceeding via transition state mechanism, that is A plus B giving a reactive intermediate AB star which gives product. Now we can take up each step of this reaction in detail as follows. Step 1. A plus B giving AB star, that is the intermediate, where AB star is the encounter pair which is formed when ions A and B approach each other, that is they diffuse towards each other in solution phase. And Kd over here is the diffusion controlled constant. Now, once the encounter pair is formed, there are two possibilities. Either it may diffuse back to give ions in solution phase, which we will take up as step 2, or it may lead to product formation, that is step 3. Now let us see what happens in each of these two cases. If the reactive intermediate diffuses back to give ions A plus B, we have the reaction AB star giving back A plus B. Since AB star is highly unstable and diffuse back into the medium to ions A and B. Now the other possibility is AB star gives product, that is step 3. Now over here the encounter pair leads to product formation and Ka over here is the activation controlled constant. Now before proceeding further, let us see why we refer AB star as an encounter pair. In solution phase, the transition state complex so formed from the reaction of ions A and B is referred to as encounter pair. In solution phase, the word collision is replaced by the word encounter. Since the molecules are surrounded by a cage of solvent molecules, these molecules are hindered from separation after an unreactive collision. Therefore, many collisions occur before the separation. Such collisions made compensations for relatively slow diffusion of the reactant molecules towards each other in liquid phase. Now, we have seen the three steps or the three possibilities for the reaction A plus B giving encounter pair giving product. Now let us see how can we define the overall rate of the reaction. Now overall rate of the reaction can be expressed as rate is equals to dP upon dt, or rate is equals to d concentration P upon dt, which is expressed as Ka into concentration of AB star, that is encounter pair. Now since encounter pair is a reactive intermediate, we can apply steady state approximation to this reactive intermediate. Now steady state approximation states that when a short-lived reaction intermediate exists in very small amount or low concentration in a system, the rate of formation of the intermediate can be considered to be equal to its rate of disappearance. That is, d AB star concentration upon dt is equals to 0. Now using these three steps 1, 2 and 3, we can rewrite this equation in the following manner. dAB star upon dt equals to Kd into concentration A into concentration B minus K minus D into concentration AB star minus Ka into concentration AB star equal to 0. Now this equation can be further rewritten in terms of the concentration of reactive intermediate as AB star is equals to Kd into concentration A into concentration B upon K minus D plus Ka. Now if we substitute back this equation in the rate expression for the equation A plus B giving encounter pair giving product, we get the expression for rate as rate is equal to d into concentration P upon dt is equal to Ka into Kd into concentration A into concentration B upon K minus D plus Ka. Now we will see the significance of diffusion controlled and activation controlled processes now. Now using this rate equation, the following two cases can arise. Case 1, where Ka, that is the activation controlled constant, has a greater value than K minus D. Under this condition, the rate expression modifies to rate is equals to Kd into concentration A into concentration B. So we find that under this condition, the rate of the reaction is dependent on rate constant Kd. Therefore, this reaction is called diffusion controlled ionic reaction. In this, the activation energy is assumed to be approximately 0 and the rate of diffusion of the reaction towards each other determines the overall rate of the reaction. The other possibility is K minus D is greater than Ka. With this, the rate expression modifies to Ka into Kd into concentration A into concentration B upon K minus D. Now, if you look back at the equation, you will notice that Kd is equals to K minus D. Over here, we considered equilibrium. So the rate equation becomes Ka into concentration A into concentration B. So over here, we find that the rate of the reaction becomes activation controlled as it depends upon the rate constant Ka. So this is an activation controlled ionic reaction. With this, now before we proceed with the classical thermodynamic approach of transition state theory to determine rate constant of ionic reactions, now let us learn about ionic strength and why we need this concept here. Ionic strength. Ionic strength is the cumulative measure of both charge on the ion as well as its concentration in the solution. It is expressed in the following manner. I is equals to half into summation Ci into Zi square, where Ci refers to the concentration and Zi refers to the charge. Now, concept of ionic strength is applicable to strong electrolytes only and not to weak electrolytes. The concept of ionic strength comes into picture as simply the concentration of a solution gives idea about the number of moles but gives no idea about the charge of ions present in the solution. So ionic strength takes into account both concentration as well as the charge effect. Now let us see how this concept is useful. Let us consider 0.1 molar NaCl solution. Now where Na plus has charge plus 1 and Cl minus has charge minus 1. Now for this, the ionic strength expression can be written as 1 upon 2 into 0.1 into 1 square plus 0.1 into 1 square, which gives a value of 0.1. Likewise, now if we consider the same concentration, that is 0.1 molar of copper sulfate solution, where copper has +2 charge and sulfate has -2 charge, the ionic strength for this solution will be different from that of 0.1 molar NaCl solution, because the charges over here are different from that of the ions in NaCl solution. So ionic strength becomes over here 1 upon 2 into 0.1 into 2 square plus 0.1 into 2 square, which in overall gives a value of 0.4. Ionic strength of a mixture of solutions can be exactly determined, but total concentration of mixture of solutions cannot be exactly determined. Ionic strength of a mixture of solutions can be exactly determined, but total concentration of mixture of solutions cannot be exactly determined. Addition of salt further alters ionic strength of a solution, although salt may not precipitate in the reaction. We will take up this concept in our next module. Also, ionic strength of solution affects the rate of a reaction considerably, and it is for this reason we have considered the concept of ionic strength over here before proceeding with our treatment for determination of rate constant for ionic reactions. With this, we will take up the classical thermodynamic approach of transition state theory to determine the rate constant of ionic reactions in our next module. So in all, in this module, we talked about solution kinetics, which is the kinetic study of chemical reactions taking place in solution phase. Such reactions are very common, but it becomes difficult to study such reactions theoretically the way we proceeded for gaseous reactions, because over here solvent plays a very important role. Two important solvent dependent parameters that are known to affect the rate constant value in solution phase are dielectric constant of the solvent and viscosity of the solvent. In general, the solution phase reactions can be classified as ionic reactions and non-ionic reactions, and over here we talked about ionic reactions. We did discuss the kinetic study for ionic reactions, A plus B giving product, where we found that the rate or the rate constant for the reaction can be found only following classical thermodynamic approach of transition state theory. That is, we found that only classical thermodynamic approach of transition state theory can be utilized to determine the rate constant of ionic reactions or solution phase reactions. We started with the study of bimolecular ionic reactions, where we considered A plus B giving encounter pair giving products. Over here, we determined the rate expression for the reaction, and we also found that the reaction can be diffusion controlled or activation controlled. Further, we even talked about ionic strength, which is the cumulative measure of both charge on the ion as well as its concentration in the solution, and is expressed in the following manner: 1 upon 2 summation Ci into Zi square. With this, we will take up the classical thermodynamic approach to determine the rate constant of ionic reactions in our next module.